Okay, now we're just going to do one or two examples of the rational functions we were graphing in the last video, just in case you need more practice on them. So we'll do this one. Y equals x squared minus 16 all over x squared minus 25. So first, factor it all out. I get x plus 4, x minus 4 on top. On bottom, x plus 5, x minus 5. Now the first step is to look for holes in my graph. Holes occur on factors that cancel out. Nothing here cancels out. So again, we have no holes. Next, we look for vertical asymptotes. Vertical asymptotes occur where the function is undefined in lowest terms, the zeros in lowest terms. So the vertical asymptotes are at x equals negative 5 and 5. Then I look for the zeros of the function. Zeros of the function occur, zeros in the numerator in lowest terms, which for us are negative 4 and 4. Then I look for the y-intercept. To find the y-intercept, set x equal to 0. If you do that, you get 4 times negative 4, which is negative 16, all over 5 times negative 5, which is negative 25. Two negatives cancel, and I get 16 over 25. So, my y-intercept is at the point x0, y 16 over 25. The last thing I care about, horizontal or oblique asymptotes. And we said as far as that goes, you look at the degrees in lowest terms. The degree here is 2, the degree here is 2. So the rule is, if the degrees are the same in numerator and denominator, you have a horizontal asymptote at the quotient of the leading coefficients. And all you do to find that is look at your original function. That's a 1, the coefficient, that's a 1. So my horizontal asymptote is at y equals 1 over 1, which is just 1. Just so you kind of understand what we're doing, if this had been 3x squared over 5x squared, your horizontal asymptote would be at 3/5. Whatever those coefficients are, just write them as a fraction, and that's your horizontal asymptote when the degrees are the same. Now I have all my information. Now I should be able to graph it. So let's see. I have no holes again, so I don't have to worry about that. Vertical asymptotes at negative 5 and positive 5. I have zeros at negative 4 and positive 4. I have a y-intercept this time at 0, 16 over 25. When you're plotting this, make sure you plot it accurately in relation to everything else. 16 over 25 is less than 1. So it's like right there, we'll say. And then I have a horizontal asymptote at 1. And again, just make sure that y-intercept is less than 1. So my horizontal asymptote is above it. We'll say it's right there. And now just plot your graph. And again, in this case, we have this 0 in that intercept. We know they have to connect, so we're good. We have this intercept in that 0. We know they have to connect. We're good. Now all we need to know is behavior around these zeros. Both of those zeros are odd degree. Odd degree, we cut through the axis, which means that this has to go down, and that has to go down. Now we find behavior around the asymptotes. That's based off of degrees. They're both odd degree. When your degree is odd, the function switches signs around the asymptote. Here, it's negative infinity. So on this side, since it's odd degree, it's positive infinity. Now I go down. Ultimately, I would hit 0, but I have no more zeros. But that works because I have this horizontal asymptote in the way. So I just approach that. Over here, same idea. This asymptote, x plus 5, is odd degree, so sign switches. It's negative here, so it needs to be positive over here. Again, I come down. I have no more zeros, but that's fine, because all I do is approach this asymptote. And there we go. A nice, simple graph. Pretty straightforward. Maybe we'll do one more and we'll put some holes in it just so we can see how to graph those. So suppose we have y equals x squared minus, we'll go with 9, all over x squared minus 6, minus x minus 6. Again, the first step, always factor it out. X squared minus 9, we all know we've done it several times, x plus 3x minus 3. Here, two numbers whose product is negative 6, whose sum is negative 1, x minus 3, x plus 2. And here, the x minus 3's cancel, and I'm left with x plus 3 all over x plus 2. Now, the important thing with this is, we only look at the polynomial now in lowest terms. Don't worry about the leading one. This will give me a whole, which we know. And as far as finding zeros and intercepts and asymptotes, use your function in lowest terms. So for this, first we look at holes. Holes occur at places that cancel out to put it in lowest terms. X minus 3 canceled out, so that's a hole at x equals 3. Then we look at vertical asymptotes. They occur where the function is undefined in lowest terms. That's negative 2. Then we look at zeros. They occur at the zeros in the numerator in lowest terms. That's x equals negative 3. Then we look at the y-intercept, because it'll help us graph it a lot of times. To find the y-intercept, make x 0. You get 3 over 2. So we get the point 0, 3 over 2. The last thing we care about is horizontal or oblique asymptotes. In order to determine that, we look at the degree. Here, the degree is 2, the degree is 2. If you look over here in lowest terms, the degree is 1, the degree is 1. The degrees are the same in numerator and denominator, which means we get a horizontal asymptote at the quotient of the leading coefficients, which is 1 over 1. So just that 1. Now I should have all the information I need, so sketch a graph. Let's see, I have a hole at x equals 3. We said save that until the end and just kind of draw a hole on. So I have a vertical asymptote at negative 2. I have a 0 at negative 3. The y-intercept is 0, 3 over 2. And then the horizontal asymptote is at 1. And again, much like the last one, make sure you position everything correctly. 1 is less than 3 over 2. So the horizontal asymptote is going to be below the y-intercept. And now we have that. Sketch the graph. There's not much information there, so if you're not sure, just pick a random value for x, plug it in, see what you get, and go from there. But you can actually figure it out, let's see, using our intuition. Right here, when I go to the left, I can go up or down. If I go down, I eventually create a 0 I don't have, which means I have to go up. And I'll just approach my asymptote. Now, behavior around this asymptote, that's based off of degree. These are both degree 1, odd degree, so sign switches. That's positive, it becomes negative. So I start down here, I hit my 0. The degree for that 0 is odd. Odd degree, sign switches, or I cut through the axis. So I cut through. That works because now I can just approach the asymptote I want to approach. Over here, well, I can go up or down, but ultimately I have to approach my asymptote. I can never have another 0, so I just approach the asymptote. And there we go. The last thing we need is our 0, our holes. I have a hole at x equals 3, and all you really have to do, that's x equals 0, so say x equals 3 is like right here. Go up on your graph, draw a little hole. And there we go. Our graph is good. One thing that I will stress, and I stressed it before when I was first explaining these in the last video, if you graph this on a calculator, it will not show that hole. The only way you'll see it is if you look at the table on your calculator, and at x equals 3, it'll say undefined, which will tell you it's undefined there and you have a hole. But graphically, your graphing calculators can't graph the hole. So do not just copy your calculator. It will not give you an accurate graph.